Okay, good afternoon, ladies and gentlemen, and welcome to your SETI Institute Colloquium series. So I'm Frank Marchis. I will be the host for today's colloquium, and I will introduce you our speaker, Burkhard Militzer. So I have a very long list of achievements for you today. Someone made a comment on YouTube a few days ago that they liked the fact that the host used to present the speaker on a small with a text written on the palm of his hand. I'm sorry, I can't do that, so I'm going to have a piece of paper for you, okay? So Burkhard got a diploma in physics at the University of Humboldt at Berlin in 1996, then did his PhD at the University of Illinois in 2000, moved as a postdoc at the Quantum Simulation Group at Lawrence Livermore National Laboratory, then joined the Carnegie Institute of Washington in 2003, and in 2007 became an associate professor at the Department of Earth and Planetary Science and Astronomy at the University of California at Berkeley. So Burkhard's research and his group, in fact, use computer simulation to understand the interior and evolution of giant planets. He will describe how they conduct this kind of simulation to extract information on the interior structure of giant planets. With this method, for instance, he explained why neon is depleted in Jupiter's atmosphere and provided strong and indirect evidence for helium rain in giant planets. In his talk today, Burkhard will briefly review the interior structure of different types of planets. He will also show his recent model of Jupiter's interior that he and his team are putting together before NASA Juno spacecraft arrive at Jupiter, scheduled for next year, if I well remember. So please join me in welcoming Burkhard.
Well, thank you so much for the kind introduction. I'm glad to be here. I had great conversations earlier this morning already. I only know about the SETI Institute actually from the more announcement in the press. I didn't know too much about the other research components. So I'm glad, Frank, for the introduction. It was very useful to me. So I would like to use today's colloquium to tell you a little about the simulations that we run. And I would like to get across what this ab initio word actually means here. And we run simulations on an atomistic scale. We're trying to make something as big as a planet, but it should be, we actually simulate the atoms. And we cannot simulate all of them. So we have a little bit of a leap of faith. All we do is essentially material physics. We tell you what do the atoms do at high pressure, and do they change their character, and whether these change of property then has an impact on how planets behave as a whole. So the argument that so we have a little illustration here. So here we have a spice slice through Jupiter, and here we have an intermediate layer where there's helium rain. And that is a proposal. We have no direct observation that this is happening. We have an indirect one, and I would like to explain to you how we come about to actually say that something is happening. So here is another simulation, sort of it's like a little snapshot, where we simulated water ice at very, very high pressure. And so we have little oxygen atoms here. These are the big spheres, and they're the hydrogen atoms in between. And the water at these extreme conditions looks very different than the water you have in your fridge. So the water in your fridge, where the oxygen atoms are aligned in nice hexagons. So at these high pressures, the hexagons that get destroyed, and these are the conditions you would find in the interior of Jupiter. And we think the ice was essential to build these giant planets because there was so much ice around in the outer solar system that they formed very quickly. So one of the questions we want to know, what happened to all the ice? You told us there must be lots of ice. You basically, to go these cores quickly, what happened to it? And we did calculations where we actually simulated whether the ice is stable or not, and the answer is no. It gets so hot and so dense in the interior of Jupiter that actually the ice melts and mixes with the hydrogen. So more in detail, if I'm not sure I will get through all these things today, but I want to talk a little about how we think giant planets formed. Then I want to give you the story about helium rain. And then I want to talk about whether these cores, we think they're there in those planets, whether they're stable or not over time. Or if it's basically like ice cream, it melts and it gets mixed with something else. And then we did a project where we thought to answer the question whether Uranus and Neptune have an ocean. We call them ice giants, and that's probably not a good name to start with, because we don't think there's actually any solid ice on those planets to begin with. But the question is whether you actually continuously dive, if you could do that, through the atmosphere of the planet. You would never hit an ocean. Or you actually hit one. So we want to do these calculations. It's basically a miscibility problem. If water and hydrogen would easily be miscible, you would just dive through and you would start from a hydrogen-dominated outer part, and it would progressively get more water-rich as you go towards the interior. Or there's a sub-sharp boundary. If water and hydrogen don't mix like oil and water, there would be. If they do mix, then it's more gradual. So that's things we can actually address with these ab initio simulations. So overall, there are two philosophies to make giant planets, and they give the very simple picture, well, name here to may say bottom up, which basically means you build something from the bottom up. You start with a core that is basically built from solid planetesimals, and they collide. And some of these collisions are so that they shatter, they destroy each other, but overall there's a net trend to basically build bigger and bigger cores. And Jack Lissauer in the audience is the local expert on doing that. So that's not what I do. But some people very deeply thought about this process, and it's now labeled core accretion, because you form your core first, and when you reach something critical, about 8 Earth masses, or a little less or a little more, depending on the details, you are heavy enough to attract hydrogen gas. So this is your picture where you first make your core, and then you attract the gas around it. And that's called core accretion, and you build something from the bottom up, if you like. And this is clearly, without question, the standard models how giant planets formed in our solar system. So nevertheless, there's a competing theory where some people say it may operate somewhere else. There's a minority will say it may have operated in this solar system, but I don't sign on to that view. And that is simply labeled as top-down. And they start with this big nebula that we have, and it builds a disk around the planet. And there's the possibility there's so many solids already ingrained in this disk that the density is so high that it could actually self-gravitate. It's similar like a giant planet would form, like a star can form. You don't need a core for a star, it just collapses onto its own. Nevertheless, in our solar system, we think that these solids were important to form the giant planets. So if you have this top-down view, well, you start with something that has solids already mixed in, and then you start settling out the core.
This
so
slide has a number 8. That number is not known.
What number 8?
8 Earth masses.
Yeah, well, it depends on the properties of the disk. If you make the disk more heavy, it's more likely to fall onto that core. And it also depends on the temperature conditions in that local area. It's not mass and temperatures. That's why I'm saying it's approximate.
It's not.
What do you mean?
It could be 4, it could be 10.
Well, that's what I'm trying to say, yes.
I think you should let the speaker talk.
Approximate is not 8.
Okay. Okay, let me just say, this is a very colloquial news. It's not, the sign is wrong. And probably the 8 is wrong. The only thing we know for a fact, the planet exists. Yes, so basically, yes.
I'll agree with that.
Yes, okay.
That's a nice constraint.
Good, yes. I'm not signing on to the 8, but I would say it's probably more than 4 and it's probably less than 20. That's at least as well we know. Okay, so this top-down view on the right, they are not putting any mass in there because we don't really know whether it really operates. We just have some indications where the left model doesn't work. So one of those is, what I'm basically trying to say is you in principle, the idea has been proposed, you settle out a core. We don't agree with this because we think in these conditions you actually have a system where you rather dissolve a core, like shown on the left here with these little arrows. The simulations that we have performed, the calculations, a core is more likely to dissolve rather than to settle out, because things tend to mix at high temperature and pressure. Nevertheless, the scenario on the right has been proposed to explain the directly imaged planets that go by the name HR 8799. They're so far, like 1020 astronomical units. They're so massive that you actually have difficulty explaining that there often was enough material around to make them. So it's not unconceivable there are other places, other solar systems where planets formed according to this top-down or disk instability scenario. In principle, you can also take a different view and say, this is something, it goes from a mixed state to a differentiated state. And then it becomes actually more tractable because we know the Earth is differentiated. So this is a nice illustration where you have an Earth core we know is iron-rich, iron and nickel. And that just exists because it basically doesn't mix with the rocks or with the mantle of our planet. So here we go from an initial state that maybe have been mixed, where something settled out. It was chemically not miscible, and then the heavier component settled out. In principle, you can also say the different view, which I showed you initially, that this helium rain business is a way of differentiation where you have something is immiscible and the heavier species rains out. It's sort of interesting because if you buy your helium balloon, it rises. But actually, when you talk about helium rain on Jupiter, it falls down. And that the simple reason is helium is light, but hydrogen is even lighter. So if helium is competing with hydrogen, the helium is heavier and settles. So and finally, if you adopt the view that hydrogen and water are actually not miscible at low temperature, you could start out with a planet that's happily mixed, and then regular H2O, water rain, could form and make an ocean. So to give the story away, we think this is not happening in Uranus and Neptune. We think they are fully mixed, and there is no ocean. So sorry, if you want to go swimming, it's not a good place to go. It's cold, but nevertheless, there will be no ocean. It will also be too dense, actually, before you reach the water-rich layer. So a little bit about Jupiter's interior. Well, we know the hydrogen is a hydrogen-dominated planet. It's about 74% in mass. Hydrogen, it has helium. It has a bunch of other elements that the astronomers take the liberty to call metals. This is probably just another lie I'm going to repeat here, but yes. So with the metals, anything which is not hydrogen, helium is considered a metal. And I would rather sign on if you go to this hydrogen, compress it very much, then it becomes a metal. But the astronomers, they like this because hydrogen, helium, everything else is just a metal. That just makes things simpler. So we think there could be about 2.7% only of these heavier stuff. Nevertheless, we want to know how much there is because it will tell us whether there's enough of a core to trigger this collapse of the gas around it. So overall, we are pretty sure it has molecular gas on the outer part that has been observed directly. It has, we know that these heavy elements are there because there was the Galileo mission dropped the probe and measured these things in situ. But it didn't go very deep. It went to about 22 bar. And the core here is about 40 million bar. So there's a lot of unexplored physics here. We know that the interior part, hydrogen, has to be metallic, has to generate a magnetic field that's not possible in molecular hydrogen. And then there's the core. And the core, as you were questioning, is the core is even less certain than we think there is. It's all based on models because we do not have a direct measurement of the core size. Before we worked on this, the standard model assumed a core between 0 and 7 Earth masses. So this is just a model that constructs the gravitational moments, which you can infer from spacecraft trajectory and the mass of the planet and the radius, and then they put all these things together. And they get something, it's at less than 7 Earth masses, massive, heavy. And we constructed a competing model in 2008, where we got a core size of 14 to 18. And it's all based on modeling, and that's where the controversy exists. So we hope that with the Juno mission on the way, it will arrive and insert in orbit July 4th next year. And what this mission will do, it will basically arrive next year, and it will be in orbit for about a year, and the lifetime is most likely limited through radiation damage. And my contribution will be to calculate the properties of hydrogen-helium as well as we can to enable the interpretation of the spacecraft data that we'll get. So what does the mission do? It will arrive here on this trajectory, has one large orbit initially, and then insert again to about 30 science orbits. And it's shown here that basically it gets very close to the surface of the planet. So that's a unique opportunity to measure the shape of the planet through the deflection of the spacecraft trajectory because of the gravitational field. So that helps us to say how mass is distributed in the interior. The deflection is slightly different when mass is distributed slightly differently. And that is the only way we can say something about the interior mass distribution of the planet. So it's from the tiny deviation of the spacecraft trajectory that it will be measured. And they can track the spacecraft, I don't know, to centimeter precisions or something. It's incredible. And then we use it to constrain the interior physics. So the orbit you see here, this in comparison with the orbits of the moons, so it basically comes in very close, and it basically it sort of has a relatively large orbit. And here in this illustration shows a little bit where most of the radiation damage will occur. So it's the charged particles are in a toroidal shape around Jupiter. So here is another sort of slide illustration how what the shape of these orbits look like. They have a very funny shape because this is sort of plotted in the reference frame of Jupiter. So, but Jupiter is really rotating underneath as the spacecraft comes by. So what do we know about the more detailed physics of the interior? I already told you that there's this molecular hydrogen here, then there's helium rain possibly, and then there is this metallic part. So I worked on a little bit on these things, and the question is whether the envelope is really homogeneous or not. And you have to come up with a mechanism to really introduce inhomogeneities, because the simple picture is you just collapse gas, it should be homogeneous. Then people had proposed that there is a first order phase transition as you go from molecular to metallic hydrogen. So this has been sort of debunked, I would say. There is a transition that certainly occurs, but nevertheless, it's not a sharp transition. So the planet should be whole mixed. It's not a good way to introduce any inhomogeneity. Then there's helium rain, and that's part of what I will talk about today. And then there is core erosion. So if you start with a solid core, and then you gradually dissolve it, the interior part would still be heavier, and the planet would not be homogeneous. So these are three things that the planet would not have a homogeneous envelope. So what's my contribution here? And it's basically something, as I alluded at the very beginning, I do something very unusual. I don't touch anything. I don't guide any spacecraft. I use big computers to predict what materials do at high pressure. And what actually happens, I solve equations. We use NASA's supercomputer time. And what we do is we basically put our nuclei, like this is hydrogen here. So the big spheres are really just like points. They have a charge. And then we ask, what do the electrons do? And that comes a little bit back to your chemistry class you might have taken at some point. So you have, let's say, a methane molecule. We know it's CH4, but what is it really? Well, we have four hydrogen nuclei here. And then there's this carbon atom in the middle. And the properties of the CH4 molecule are really determined by what the electrons do. So what the chemists like to sort of draw these nice orbitals around it, the electron cloud, if you like. And that's what I do. I have a big computer code that calculates these orbitals called for every position of the nuclei, shown on the left. We do this for 100 to 200 nuclei. Then we calculate the forces on those nuclei, and then we move them a little bit, and you recalculate those forces, and we follow eventually Newton's laws. And it's all the computer time goes into deriving these orbitals, And we talk to the physicists and we take all their good ideas, and they gave them funny names like local density approximations and general gradient approximations, all these things. And we try to get the best orbitals possible because they tell us how compressible hydrogen is. They fight back. If you try to compress hydrogen, there will be a resistance because these orbitals don't like to overlap. And that's what we like to characterize as well as possible. So you can say this is all black magic. Doesn't work. Come on, you can do these things, whatever. And well, we have to prove ourselves to some extent. And now our experimental colleagues. And they do these things. They want to understand hydrogen from a different point of view. And they have a big gun or a big laser, and they compress these things dynamically. They run a shock through the material. And they can, for a very, very short time, like a millisecond or a microsecond time scale, they generate a state of high pressure and density. And what I'm comparing here is, so what they did, they have a model, and it was designed to mimic the outer parts of Uranus and Neptune. And they called their molecular mixture synthetic Uranus. And they basically compressed this in a shockwave experiment. And what they told us, in the shock, this mixture of oxygen, carbon, and nitrogen atoms and hydrogen became 2 grams per cc. That's twice as heavy as water. It reached a temperature of 3,000, and the pressure under these conditions was about 50 GPa. So this is 500,000 bars. So now I say, well, this was a hard, difficult, and expensive experiment. And we want to now see how do computer simulations do. And we packed the similar number of carbon, nitrogen, oxygen atoms, and hydrogen in our simulation cell and solved these equations I just tried to allude to you. And we prescribe what the density is. And we give it a temperature. And we got 52. You say 52 is not 50. Where is the difference coming from? That's what we're talking about. So they have to do these we basically solve equations, they do the experiments. If the experiments were perfect and they could do the experiments for all conditions in the universe, I wouldn't have a job. But they can only do a few measurements and we still have good things to do. So what I did here in this case, basically I prescribed the temperature and the density, and my pressure was a little too high. So I went back to their measurement and said, they didn't exactly know what temperature was. They gave an error bar of plus minus 200. See, 200 here, I'm actually a little bit more precise. And I lowered it within their error bar to 3,220, and I got very, very good agreement. So we call this, my computer simulations are in very good agreement with what they measured. So I'm not the only one doing this, there are other groups. Here's a beautiful comparison with, for water. So these were very challenging experiments for water. These were the points that were measured in the pressure density space, and here there was the reshock when they shocked it again in the same experiment. And the lines here, the red line and the beige line, they almost perfectly agree with it. So this is basically, I claim we can characterize materials very well under these conditions. So that's what we always have to justify. So what have we done? We basically applied this to molecular hydrogen. Then this is a snapshot from the simulation here. We have bonds, and the electron cloud is given by this little sphere. And if you then compress it, you actually make metallic hydrogen. It's simple for us. It's very, very challenging in the experiment. It's just because there's not enough space for these molecules to exist. So we use these, we have done a lot of calculations here, and then we put it all together to make a model for Jupiter. And our model in 2008 predicted a massive core. So in this diagram, you can just look at it or you can listen to what I explain. Our core was between 14 and 18 Earth masses. And other people basically predicted the core should be within 0 and 7 Earth masses, and there should be a lot of ice. So our model basically predict that we have relatively little ice in the outer envelope, and we have a massive core instead. So if you plot this in this diagram, we are up here with a massive core and the a light envelope, and the other competing models are more like here, where you have a lot of ice in the envelope and a very small core, even 0. And then you have trouble making that core unless you invoke core erosion. If you say there's no core on Jupiter, how do you make the planet unless you sign on this other scenario?
I'm trying to understand this. On your models, you're saying you cannot be in that other region of parameter space?
Yes.
It's impossible for you to get there?
Yes, there are a few wrinkles with this, yes. So we are all up here. So what the other models that were constructed, they basically assume there's helium rain, there's a different helium abundance, which we didn't do. That's actually a very useful concept, but we didn't believe in it because there was very little evidence at the time that it would actually operate on Jupiter. Now we have changed our minds since then, and I will give you an update on this. So what we had trouble with, and I admit this, the 2008 model could not match the gravitational moment J4. It had been measured by the spacecraft trajectory, and we could not get a good match. And we could only match it by another unusual assumption. We assumed that Jupiter rotates differentially on cylinders. It's very strange. So the planet Jupiter is not a solid body, we're saying. You know you have jets on the surface, but we're claiming, and we just made that up, basically that you have differential rotation. It's not completely unconceivable because the sun does that. So in our model, to match J4, we assume that you have these deep interior winds to match J4. So we're not sure that is true, but there was one way out to match J4, which we couldn't match otherwise. Okay, so that was in 2008. Things have changed a little bit. So to talk about helium rain, we start by the observations from the Galileo Entry Probe. And it's literally, there was a Galileo mission, it dropped something in Jupiter and measured the abundance of everything else besides hydrogen and helium. And then it eventually became too hot, and then the probe just stopped functioning. But we got wonderful data for the time. So, and what people plot here is basically what did it find compared to the sun? We thought we knew reasonably well what the sun was composed of, but you think all of this gas had like heavier stuff mixed in. That same gas formed the sun as well as Jupiter. They should be identical. Well, that didn't come out quite right. So you had about, read this diagram is you have carbon atoms, you have 5 times as many carbon atoms on Jupiter compared to the sun. Well, how do you get carbon atoms in addition onto Jupiter? Well, we know about Shoemaker-Levy. You can always have comets impacting and enrich the envelope. So anything make it richer in these heavy stuff is not hard. You always invent a few more comets and then you're okay with your model. The only problem is how do you get rid of something that's already in Jupiter's envelope? So there's helium, that's basically slightly depleted, and then there's neon. Neon is the orphan child, or whatever say it is 9 times less on Jupiter compared to the sun. So if you adopt that view that they're both made from the same stuff, you have to wait to basically suck the neon atoms out of Jupiter. And that's what, it wasn't our, it was we followed Stevenson and Ralston. They said, well, maybe helium rain has anything to do with it. Well, helium rain is basically that argument that as the planet cools, it reaches a regime where helium and hydrogen behave like oil and water, and one separates from the other. And this is shown here in temperature density space according to these ab initio simulations that I do. Someone calculated, Miguel Morales, who I know very well, he calculated where this should happen before we have good experimental data. So then the helium would rain out, and gradually you would remove helium from the upper part and enrich the lower metallic part. So what we did, we ran these calculations, and we could calculate the energetics of putting a neon atom in hydrogen or putting it in helium. So that's the assumption we set. We said there is helium rain. And now assume what would a neon atom do? Is there a strong preference for this neon to go into the hydrogen part, or would it prefer to go into the helium droplets? And once it's helium droplet, it's going to rain out. And we actually found a big effect. So we found these curves shown in the red here. I'm showing some, it took us some while to figure that part out to make it efficient. But basically, there is a very simple answer to sort of cast all the complicated physics goes in here. And that basically tells you if you try to put neon into hydrogen under these conditions, it is perpetually not happy. And that relates to the orbitals in the neon and the orbitals in the hydrogen with all this complicated physics, but the story is very simple. It takes up a lot of space to put neon in here. If you stick it, on the other hand, in helium, it's much happier. Neon and helium, they're both noble gases. They like to hold on to their electrons. They're much happier there. So therefore, there is a strong preference. If helium rain exists, there is a mechanism to get rid of the neon in Jupiter's atmosphere. So the Galileo probe measured there's a lot less neon, and we have just an interpretation of that data. And now we can also say, well, if that's true, that is an indirect way of saying that there is helium rain occurring on the planet which we couldn't detect directly. Well, people liked that idea, so there were a few press reports about it in various languages here. Some were sort of interesting. There says helium rain explains scarcity of neon on Jupiter. But already here you see that the scientific story was actually used to draw attention to the sort of the embezzlement scheme in the British cabinet that was going on. We also got cited on other websites here where helium rain fits right in the series from the mysteries of the ancient civilizations to the UFO. Helium rain fits right in there. And then I have to admit, Bill Gates beat us. He was named #1 because at the time he was building small nuclear reactors. We didn't even make #2. #2 was someone who was building portable mind readers. But helium rain is already 3rd in that list. Okay, so another project that we engaged on was basically on another mixing problem. And iron and rocks don't mix, at least for the Earth. We know that from the density observations, from the free oscillations that we observed, we have a big iron core, and it would not exist if it would be happily mixing with the mantle rocks. There is some iron in the mantle rocks, but it's not very much. So we ask, just keeping in mind that exoplanets are huge, much bigger. They're terrestrial, they're basically rocky, and when they form, they're much bigger. And a bigger planet, in almost all cases, also leads to a hotter interior. You want to know, is there a rocky exoplanet where the iron and the rocks are not differentiated because simply it's too hot? That was one of the things we wanted to know. How high or how big would that planet have to be? So we did simple calculations. We basically wanted to know what's energetically preferred. And that's a little bit of a diagram. We call this a mixing diagram. And what we say at low temperature, well, low is, in our case, 5,000 degrees or 4,000 degrees. The things form their separate material. So this is like we calculate the Gibbs free energy, which is sort of a mixture of different energy terms that I'm splitting here below. But the simple story is at low temperature, iron and rock will not mix. And then there's this critical transition around 6,000 Kelvin that we calculated, and they would no longer mix. So if you put it all together in a sort of a miscibility diagram, then you have something that very much looks like oil and water. If you look up the oil and water phase diagram, it basically has a gap here. It's called the mixing gap. And that tells you that if two fluids at low temperature are immiscible, but there's always a little bit of oil in your water, and there's always a little bit of water in your oil, even if they don't like each other. And if you don't trust me on this trend, you should take a sip of the water next to the big water horizon accident that may happen. There is always a little bit of oil dissolved in your water. So nevertheless, what we calculated is a prediction how big an exoplanet would have to be for these things to mix. We had difficulty assigning a size. So here at high temperature, everything will mix. And here it's basically so that's actually mislabeled. So this should be, that part here is miscible, and here it's immiscible below. But we had trouble really assigning it to a specific size of a planet because it's not clear how planets really get, how hot do they get when they form. So another problem we tackled with these simulations is the question whether ice would actually remain in solid form in Jupiter's interior. So I try to argue that this ice was essential to build the core of a planet quickly, but then you pile the hydrogen on top, and you ask the question, what would happen as this hydrogen basically falls in there? You have a lot of energy, it gets very hot. Would the ice remain solid or not? So this is like another mixing problem we can do. And what we did, the calculation, we calculated the Gibbs free energy of hydrogen, and then the Gibbs free energy of water. So the water, that got us distracted us slightly because the state of water was not known at these conditions. This is like 40 million atmospheres. So in this case, we just looked what is a possible water structure, and we made some predictions, and we calculated what's the energetics. And then we compared that state of these two materials being separate to the energy of them being mixed. And the assumption was that, there's so much hydrogen, you get away with just putting one oxygen atom in hydrogen. You can look what the energy is. And we put this on a diagram where you have temperature on the y-axis and pressure on the x-axis, and then you have the cores of Jupiter and Saturn. So Jupiter, giant planet, it's 40 million atmospheres, and Saturn is a little smaller. It's around 15, basically. And that depends on the model. Yes, I admit there is an error bar once again. So this is, we did these calculations, and what we've predicted based on this is basically that ice, it takes only 3,000 Kelvin only. This is, of course, huge by today's standards or ambient conditions, but basically in 3,000, ice becomes unstable. So therefore, there is no ice that is stable in Jupiter's core. It's all far too hot. There is core erosion as a result. So we went on, we basically calculated these same calculations for rocks. We took silicates, MgO and SiO2, quartz if you like. We also basically did the calculation for iron. And all of those shown here in this diagram are not stable. Jupiter's core is too hot, or the conditions in the hydrogen is too hot for any of those core materials to be stable. So they all melt, they all mix. The question is, would there be enough energy to get this heavy material up? So we thought the planet would be completely homogeneous, and other people just, no. There is a reason the core is there. That is the point of lowest gravitational energy. If you're claiming these things are gravitationally unstable because so hot, you have to basically provide energy to get this heavy iron core and the rocks up. And it's not clear whether there's enough energy available in this planet. So it's even the planet, the rocky core dissolves. There may not be enough energy actually to bring it up. And there are cases where this exists on our planet where something like this happens, and you have to go dive in the bay. And there are sometimes layers that have different salt concentrations. They should be mixing, but basically there's a gravitational force, and they have different temperatures, and they're layers. And they're relatively stable. And the same thing has now been proposed for Jupiter. That they told us, sorry, yes, the core is unstable, but what we think is happening, you have layers as a result. And people are arguing now how stable these layers are. It's a not well understood problem. We did one part, we said the cores would like to mix, and the dynamic part, whether there's enough energy for these things to mix up, is not clear. So maybe Juno will put us some constraint, but basically this picture may be a reasonable answer, that you have many of those layers. They talk about 100 layers. And I said, what? When I started these calculations, there was a core, metallic hydrogen, and molecular. There was 3 layers if you counted them. And now they already went their models where they basically said this could be 100 layers. So we need some additional constraints from spacecraft, because this is another model where we do not have enough data to constrain.
The ices could be in those layers too, or the ices you mixed?
The ice, there will be a different ice concentration in every layer. It will be denser here below, and it will progressively get lighter. But it's never ice in any form. It's always oxygen atoms or carbon atoms that happily mix with the metallic hydrogen. So one very unusual way, are actually free oscillations in Saturn's rings, which I thought is another constraint on the planetary interior, which I thought is incredible when I heard the first time. So you've all seen pictures, and go upstairs if you haven't, of Saturn's rings. They're remarkable, they're beautiful. And there is a lot to be learned from them. And I'm not the expert in rings. I'm just repeating what I learned by listening to other people. And one of the remarkable things, what basically happened is that these C rings, there are slight density waves in the C ring. And that is sort of on a tiny scale, the density of material in this ring has these characteristic spikes. So they should be perfectly smooth here, but there are these characteristic waves, if you like, where the material is a little bit more dense. And the only way that was figured out is basically through occultation, where you basically, this Cassini spacecraft looks how much light actually goes through the rings and then finds teeny tiny oscillations. Well, they wouldn't mean anything to me, but other people are really, really smart, could identify this tiny signal, and they came up with beautiful results. And they said that these oscillations have nothing to do with the moon. That's what they first have to do. If you have a big moon, that can steer things up, that makes trouble. But if you don't find the moon, you basically have to come up with another scenario. And what they came up with is that the planet has free oscillations where it just basically rings like a guitar, if you like, and the Earth is doing this. And that basically a guitar string has a characteristic frequency and depends on how much you tighten it and how heavy it is. And the Earth is the same thing. How heavy is it and how tightly are the different materials coupled? And if you understand that part well, you can learn something. If you know the frequency, you can learn something about your guitar. And now they're saying this, well, I have these oscillations here. And I claim this is not a moon. This tells me something about the interior of Saturn. So now people construct models for the interior of Saturn to match these frequencies. They're not just one, there are quite a few of those. And basically the one model that has been proposed, I'm sure it's not the last one, but Jim Fuller basically worked on this. And he just published in Icarus last year. And he said he can only make these rings, can only explain these unusual frequencies and why the modes are split. Well, you know, it's like, you know, your guitar string, you tune it by aligning these frequencies. But frequency alignment resonances are very easy to identify. And he basically found that some of those modes, there should be just one, but he found two. And his explanation was, well, I can split these modes if something is stratified in the interior. So stratified means the planet is not fully convective. So, and that is sort of another constraint. There has to be an explanation. If you tell me the planet is stratified, then somehow this has to be of different material. It has to be, maybe it has to have more ice, or it has to be metallic, or it has to be some other property. If you just tell me it's metallic, I ask you, why should that be? Normally, a planet is fully convective unless you invent something. But here we seem to have evidence that something unusual goes into Saturn's interior, and this gives us some extra homework to do. So what else did we do? Another project relates back to whether hydrogen and water become miscible. And this phase diagram is very well understood at low pressure. Just the question is what happens at high pressure. And we started this because there was a paper published in Nature that did the following. They wanted to see whether hydrogen would actually mix with rocks. And you know, water is very essential for volcanism, for example. You have subduction, rocks that have a small fraction of water go down and it melts below and it triggers volcanism all over. So it's important for geophysics. So what they did an experiment with lots of rocks and they mixed them with water and then heated them up. And as a result, there was some reaction with the water and some hydrogen was produced. And then they cooled it back down and they looked at these bubbles. That's actually a picture from the paper here. And they said, what happens to those bubbles? And what happened is they took statistics for different pressure and temperature conditions. And they basically said, look, here, this is temperature and this is pressure. And basically said, when we didn't heat it enough, we always had preferentially water bubbles or hydrogen bubbles. We didn't have bubbles that were mixed. And then they repeated these a bunch of times. And then when they went above a critical temperature, they have bubbles that were mixed. And not mean when they cooled it back down, there was a water part and the hydrogen part. But they said initially during the experiment, these things were miscible. And only when we cooled down, they basically formed these separate bubbles. While here, When they didn't reach this, they basically claimed that they were either completely water bubbles or just hydrogen bubbles. So I'm just regurgitating what I learned from our dedicated work of experimentalists. They're very hard experiments to do. And what they predict is basically the following. They drew this red line through this and said, well, below, hydrogen and water are not miscible, but above the line they are. That was based on the experiment, and they are the experts in the field. So we tried this. Is interesting. If you extrapolate this line, you could actually say something about Uranus, because Uranus, the adiabat may go up through here at some point. If you just take this literally, there would be an ocean on Uranus where water and hydrogen become immiscible. So we did, one of the postdoc, François Souberon, did very dedicated calculations. And here you have a snapshot from those, where you have the water molecules shown here, and you have the hydrogen here. And he calculated whether they would mix or not. And surprisingly, we could not reproduce the experiments. In our simulations, they always mix. So this is sort of a little bit controversial, because you would like to have an experimental and the theoretical results be identical. No, in this case, we don't. So, and then we have to, so the theorists basically like to tell the experimentalists what they've done wrong, and vice versa. So in this case, they put certainly the finger, they will come back to us, but our paper hasn't come out yet, so we haven't heard from them. But basically, we told them, can you please repeat the experiment without rocks? And that, I think there's a valid argument to make. I'm happy to admit my simulations are not perfect. There are always some approximations. Many times they work, but the experiment is bulletproof. But they have rocks in there, and I think that's what not we were interested in. There is a rocky component, but it's very deep down in Uranus and Neptune. There's nothing to do with whether it's an ocean or not. So, however, you could sort of take that view and say, let's hope we trust the theory for a moment. And let's say we observe an exoplanet that has 4.5 radii, Earth radii, and 10 Earth masses. What would you say? Well, what do people typically say is they say, well, we have a mass radius diagram here. We have a pure iron planet, we have a pure silicate planet, we have a pure water planet, and we have a pure hydrogen-helium planet up here. So if you find something in between hydrogen, a gas giant, and a water planet, you can just argue, if you like, well, it has a core of 2.4 Earth radii, and I add 13% hydrogen. And that's a perfectly valid model. You just have a water layer, and you have a hydrogen layer on top. And that tells you how much hydrogen there is. And then people come along and say, okay, 13% hydrogen. I want to make an evolution planet. I want to understand what were the conditions to make a planet that has so much water and 13% hydrogen. Well, if you adopt the other view and you say water and hydrogen could actually mix, you could make a homogeneous planet, and then you have a way to fit 25% hydrogen. That is just a different way of interpreting things. I'm not sure of saying that this is the full final answer, but our simulations predict water and hydrogen mix. And as a result, there could be some hydrogen deep down in the planet, and that has much higher pressure, and therefore there could be hydrogen fraction overall could be higher. So to conclude a little bit, I want to come back to this Jupiter problem that we worked on. And in particular, since 2008, we had a lot more time to do more refined calculations, how Jupiter and how helium and hydrogen behave under high pressure conditions. And what I'm showing here, the points are all the calculations. So you can trust me, every single point here was run on a NASA supercomputer with at least 100 cores, and I don't know, for 2 days up to a week. So your taxpayers' money that funds these NASA centers, all the electricity, basically we use it to calculate what do those planetary materials behave like. So there's a lot of computer time and also a lot of human time that goes into that. So I think for this calculation we burned 8 million hours, which is, I think, at some point I estimate this is like 100 cores for an entire year. So, well, they have big machines now. I'm not the biggest user, but at some point I had like 4,000 cores that I was using at the time. So, and that's all thanks to the the Bay Area that make these things happen. So yes, we use these things. Okay, so we find something. The people with the blue line here, with the blue dashed lines, they made their model without computers, almost. So they had as much as computing power as your cell phone has. So they couldn't calculate many atoms. They just had to guess what would molecular hydrogen be like. And they did a wonderful guess, actually. They did it with beautiful analytic work. And we agree with them in most places, except for those errors. We actually calculate a huge difference. And as a result, our models are different. So we're basically working on a new model. And again, we find a huge core. It's not, this is what we've done in 2008. I haven't updated the graphics yet, but we find about 12 core masses, 12 Earth masses of a core. And we attribute this to this change. Our equation of state for hydrogen-helium is different from what people used before. And that has an impact on the estimate of core size for Jupiter. So we're putting together a new model. It's slightly different what we've done in 2008. We have more accurate value of the adiabats. We now assume helium rain, which we did not do. And we get, again, a massive core. It's not quite as high as 16 Earth mass. We have 12 at the moment. And we get rid of this rather unusual assumption of differential rotation. It could still happen, because I just learned this morning, it's very hard to slow down a core. If you start with differential rotation, you just have gases. They could be spiraling at different rates forever, in principle. But it's still a little bit of an unusual assumption. So we're not making this in today's model. So we still get a large core, which we attribute to a different equation of state. So to summarize the talk overall, I hope I showed you some illustrations that helium rain exists on Jupiter, even though we cannot observe it directly. I used computer simulations to claim that of all those core materials, ice, rock, and iron, they all dissolve. We're not sure whether the cores have really eroded completely, because we're not sure whether there's enough energy available to bring this heavy stuff up. And Juno will hopefully put some constraint on this. I claim water and hydrogen are happily miscible. I don't trust the experimental results, but I'm sure they will do more experiments now to prove us wrong. So it will be good for everyone. And we have a latest an update to our Jupiter model, and we still get a massive core, and we stick to it. Okay, thank you.
Thank you very much. I have a lot of questions, but there is questions in the audience as well. I'm going to ask one first. You show that the new model that you have give a good agreement with the J4. I thought we could compare we could better understand the interior of a planet like Jupiter if we study the magnetic field. Can you get information from that, such as the structure of the magnetic field, for instance, will be better known with Juno? So will it be possible to compare the structure of the magnetic field with your model?
Yes, so let me first say Juno will measure the gravity field, it will measure the magnetic field, and it will also measure the oxygen abundance through radar measurements. And the magnetic field is very important, and we get much better. We'll understand Jupiter's dynamo much better. There's no question about it. But dynamo models, if you ask how well can you really model a dynamo, made a prediction and constraint, so there's this much metallic hydrogen, otherwise the magnetic field wouldn't match. That is unfortunately very difficult. So we in principle understand how magnetic fields are generated, but the details are difficult to quantify. And there are more uncertainties than we have. So yes, it's possible, but there's so many other parameters you can turn that you can always change the magnetic field. It's hard to really say, to relate this to the J4 measurement.
Okay, so Juno that will do magnetic field and gravitational field may provide the data that you need to refine the model.
Yes, the question, but it will always be a model. It will never be model assumption free, yes.
Okay, thank you.
That was a very interesting talk, but one of the things you do in your model is you don't talk about the elements in the Earth crust that are common, like silicon, calcium, aluminum. and they form the feldspars rather than the olivines.
Yeah.
Why does your model not include these very common elements?
So the Jupiter model? You mean the Jupiter model?
The Jupiter model,
Yeah,
yes.
yeah. So let me just say, I'm in the Earth and Planetary Science department. So I have colleagues who study rocks, and I have students who work on these things. So we worked, for example, we calculate elastic properties to figure out how fast seismic waves travel. So I do some of that work. So now if you want to put in a, put together a Jupiter model, the details are often not important what materials you put in. And specifically, I'm trying to argue, we just add the ices because we believe they were the dominant species, and we could add silicates and other materials. And then, well, let me just say, the simple answer is, if you put feldspars and all the other things in Jupiter's core, they will dissolve. So it's basically it all matters what atoms are there. It doesn't matter whether it was a feldspar or some other model, it's just the mass is the most important element. So I'm trying to say that the atoms exist in a very different form, and it doesn't matter whether it's a feldspar or another common mineral. The property of that mineral is lost when you put it in metallic hydrogen. And we just, okay, I admit with you, the models we're constructing at the moment, they use typical ices. But I agree with you, yes, we should add more rocks, and we're working on that. But the simple answer is at the moment, this will be a small correction, and the physics of those details will be lost once you put it at high pressure and temperature.
So it makes no difference whether you have magnesium or you have instead silicon, for example, in your model.
It will not make a big difference. I will test this, but that is my simple answer for the moment.
Both Jupiter and Saturn are thought to be fully convective. How do those convective motions change any of this?
So that is a controversial point. Yes, it's all models, they model the heat flux, they measure how much comes out, and that is consistent with a fully convective envelope. So then someone comes along and says, well, you need to have helium rain. Otherwise, we cannot, that was actually the triggering point. Saturn's excess luminosity was the reason to invent helium rain, because they wanted a mechanism to produce more heat. So then the question is whether you have helium rain that you can argue, as Stevenson did, that will not perturb the convection pattern too much. And then other people take a different view. Say this is convective rain is just introduced such a strong barrier in composition that it may not be fully convective. And then there are people, as I've shown here. So basically in the picture where we have double diffusive convection, it goes by here. They argue that you only have convection in every layer separately. And then you have diffusion across. So this is all possible. Nothing has been ruled out. I would just say we have a model that sort of works. And you can always come up with an alternative saying, I make it more complicated. And then maybe not all planets are fully convective. I wouldn't sign on to that completely.
Very good talk, inspiring. I'm KRS Murthy. When you say metallic hydrogen, what are the properties of metallicity that you're assuming and comparing?
Yes.
No, belabor on the question, but we can get into it.
So metallic hydrogen has been a sort of an important subject. And the reason is if you have molecular hydrogen, it's not electrically conducting. You cannot make a magnetic field. All magnetic fields are generated because you have a conducting fluid that convects, and then you have currents driven in that field. Those currents trigger the magnetic field. So if you claim there is no metallic hydrogen in Jupiter, we have no way to explain the magnetic field. So that's the evidence.
So it's the electrical conductivity that you're looking at in the metallicity part.
Yes, that's what we mean when we say it's metallic.
Okay, just want to make sure.
Yeah. So for so basically, yeah, that is the yeah.
Hi. Thank you. That was really interesting. you may not have run these calculations given the enormous amount of computing time, but I was wondering, since all your charts are like temperature versus pressure, the assumptions about temperature, I started thinking in terms of the Nice model, and maybe Jupiter was further or closer, but also exoplanets like hot Jupiters and things like that, and how radically different temperatures or radically different distances from a sun over time would affect these interior calculations.
Yes, so that was what you assume, and Jack Lissauer is sort of the expert to ask this. If you put together a formation model, and the assumption is it should work for the solar system, and then you assume different conditions, but the principal model may work for exoplanets too. So you can find planets that are basically much more massive, and then the surface to volume range was just less, and they didn't have much time to cool, so they're just much hotter in the interior. So we would put together an equation of state. You could model these planets. So the irony is temperature doesn't matter that much. If you have a puffy planet, for hydrogen and helium it does matter, but for rocky planets it's a small correction. So we provide these equations of state, and but to be fair, other people had simpler models. So I run these super calculated to get these materials models very accurately. And then, but other people had something before that was sort of captured a good part of that physics, and for studying exoplanets, it's often good enough. So that's how it's. I think we hope that our new equations for hydrogen and helium will actually help to understand exoplanets. But you always have observations with a certain error bar that would you may not need these highly accurate calculations because the precision of your measurement isn't that high. So.
Now you've gone to hot and more massive Jupiters, exoplanets. Can we push these equations of state into this other realm of substellar objects, the brown dwarfs and that kind of thing, the giant planets, brown dwarfs, substellar? Or are there better ways of looking for the equations of state there?
No, I think we claim our equation of state is the best one available in that regime. Yes. So if you go back here, where did I put this? So in this regime, at high temperature, so where would we put this? Here. So we find, when we calculate, there's always Sumo and Chabrier, which is the established workhorse model. And we just look for the corrections because the model's pretty good. So we found this regime here below, which relates to Jupiter and Saturn. But there's also this regime up here where there's a correction to the equation of state here as well. So there's two big regimes, and that may apply to brown dwarfs. So we have not fully there are uncertainties in these models because and nobody has actually used this and to make a better model for a brown dwarf. I can calculate these conditions, but even brown dwarf models have uncertainties. So the short answer is yes, this is our equation state is applicable there, and if it's not, I can run higher temperatures, no problem. And it is slightly different from Sumo and Chabrier. We're just not sure if it's different enough to change our understanding of white dwarfs. That's where it hinges, I think.
Okay, Burkhard, thank you very much. I can see that to run this, you do a lot of calculation on computer. So most likely when the computer is running, you don't do anything, right? You're looking at the screen and you're drinking coffee. So
wow.
That's a cup to remember the SETI Institute and you talk here. Thank you very much.
Oh, thank you. That's good.